Intermolecular forces. These are the forces that hold condensed states together. Condensed states are solids and liquids. The strength of these intermolecular forces depend on the structures and the properties of the individual particles. Whether a sample of matter is going to be a liquid or a solid at a particular temperature depends on the relative strength of the intermolecular forces compared to the amount of thermal energy that the particles have. So if we have strong intermolecular forces, the melting and boiling points are going to be higher. If we have weak intermolecular forces, we're going to have lower melting and boiling points. I think of intermolecular forces as stick-togetherness, or you could also think of people or objects covered in Velcro. Okay, and so how sticky the Velcro is related to the strength of the intermolecular forces. These forces come from interactions between charges. Okay, some of these charges are permanent charges, like between ions. Some of them are partial charges, like we see in polar molecules, and some of them are just temporary charges that come and go. So we need to remember Coulombs Law. This is the full Coulombs Law, where 1 over 4 pi epsilon is a constant. But the really important part here is that the energy, the potential energy of two oppositely charged particles is proportional to the magnitude of their charges and inversely proportional to the separation between them. So we refer to this a lot. The energy is proportional to Q1, Q2 over R. So if the magnitudes of the charges are greater, the force of attraction is larger. If the distance is smaller, the force of attraction is greater. Okay? And we've looked at that before. When we have actual bonding, which we've been talking about, we have large charges at very close distances, and so bonds are strong. Here we have a water molecule. There's a covalent bond between an oxygen atom and a hydrogen atom. The distance here is 96 picometers, and this bond is going to be strong. Intermolecular forces are between molecules, and so the distance between the charged objects is greater. Here, there's an intermolecular force attracting the hydrogen of one molecule to the oxygen of another, but the distance here is more like 300 picometers. And so because R is so much larger, intermolecular forces are always going to be weaker than actual bonds. Okay? So there are 4 different types of forces that we're going to talk about. The first one is the dispersion force. This has several other names, so I'm just going to write these up here for you. Oh, I already wrote that one in there. Never mind. It's also called a London force. It's sometimes called induced dipole force. That's my favorite name because it's more descriptive. It's also called van der Waals forces. So if you see any of those names, they all are referring to the same thing. I'm going to try to refer to it as the dispersion force because that's the term your book uses. All molecules and all atoms have dispersion forces. Okay? This is a result of electron fluctuations in atoms or molecules. So here we're looking at an illustration of an atom. What element is this? Helium. We can tell because there's 2 electrons and 2 protons, so this is an atom of helium. Now, helium atoms are not charged, right? We've got 2 electrons, 2 protons. There's no overall charge on this helium atom. And we talked a lot about what these electrons are doing, and we basically said the easiest way to think of it is it's like a standing wave. The electron's in this standing wave somewhere. If we take a snapshot, we could pinpoint where those 2 electrons are. Then we don't have any information about how fast they're moving or what direction, but we could take a snapshot of them. And so we might see here that there's, kind of on opposite sides, and here they're on opposite sides. But then sometimes when we take that snapshot, we might find that they are both on the same side of the atom. right? That's not going to be a normal occurrence, but it can happen. And so this reminds me of a time when I came into the living room and all 6 of my kids were sitting on half of the couch. They were just all piled on top of each other. I don't even remember why. I was just so surprised, because usually they're spread out all over the place. They're not even always in the same state these days. They were all just piled up together. It lasted about 2 minutes. I got one picture, and then it went away. That's like what happens with electrons. Normally, they're just spread out, kind of generally spread out equally, but sometimes they can get lopsided. So if both of the electrons are on this side of the atom temporarily, then this side of the atom is going to have a partial negative charge. And the other side, where there are no electrons, is going to have a partial positive charge. Does that make sense? So the atom has become electrically lopsided. It has what's called an instantaneous dipole, a temporary dipole. It's not going to stay that way. Those electrons are moving. They happen to be on the same side right now, but in a fraction of a second, they're going to spread out again. So at any given instant, the electrons in any atom or molecule can be unevenly distributed, giving rise to this instantaneous dipole. Well, if one atom has this temporary or instantaneous dipole, and there's another atom nearby, the partial positive charge on this side of the atom is going to attract the electrons on the neighboring atom and cause this atom to get lopsided also. Does that make sense? So this is Alcatraz, and no, actually, this would be better. I keep modifying these things as I go along. So we have 2 sightseeing boats out on the San Francisco Bay. And on this boat, maybe because people got a glimpse of Alcatraz or something, all the people went to that side of the boat. Okay, so the boat starts to tip a little bit, and in this nearby boat, people start to notice that boat's tipping, and so everybody goes over to the side to see. Look, that boat's going to tip over, and now their boat starts tipping. Does that make sense? That's kind of what's going on here with the electrons. This one getting lopsided induces the one nearby to get lopsided. Now we have a partial negative charge here, partial positive charge there. There's an attraction. That is the dispersion force. It's an attraction between 2 temporary dipoles in neighboring atoms. And then those temporary dipoles disappear, and that dispersion force also disappears. Does that make sense? So this is a very weak force, because it comes and it goes, and we only have partial charges here to start with, so it's a very weak force. But all atoms and molecules do that. The magnitude of that force depends on how easy it is to push those electrons around. How easily does the molecule or the atom get lopsided? And it turns out that's related to the size of the atom or the molecule. If we look at the noble gases, helium is the smallest, and they increase in size as we go down the periodic table, and xenon's the largest. In xenon, those outer electrons especially are much farther from the nucleus, and so it's just kind of like a big jello. I think of it as, sort of a big jello-y, flabby atom, right? And this one, helium, where there's 2 electrons on that inner energy level and they're just tight in there, this is more like a hard little marble. This is easier to distort the electron cloud. So this one can get lopsided more easily, and so it happens more frequently, probably, and then the magnitude of the charge is larger. And so we see that dispersion forces are stronger in larger molecules or larger atoms, okay? And one of the things that we observe as a reflection of strength of intermolecular forces is boiling point. Helium boils at 4.2 Kelvin. Okay, that's 4 degrees above absolute zero. It's really hard to get helium to condense into a liquid. As we go down and the size of the atoms increases, the boiling point goes up. That's because the intermolecular forces, the stick-togetherness is greater. So imagine a bunch of people wearing Velcro suits, right? and you just, you all come together, maybe a big group hug or something, and then you're like, you're stuck together, right? How do you get unstuck? Energy. It takes energy, and if you're really stuck, you might have to rock back and forth a little bit and build up enough momentum to peel the Velcro away. The stronger the Velcro, the more energy you need to get away, right? The stronger the intermolecular force, the more thermal energy, the higher temperature is needed to melt or to vaporize the substance.
So do you have to, like, for example, for helium, would you make that into a liquid first and then have to boil? Or how does
To
that
measure the boiling point of helium, yes, you'd have to condense it into a liquid first.
And how do you even do that?
You get it below 4 Kelvin. Get it really super, super crazy cold. And they can do that. Yeah. It's not something we could do in the lab here, but it can be done. All of these boiling points are crazy low. Any other questions?
I have a question.
Mm-hmm.
They put a piece of metal on dry ice, it's really cold.
Mm-hmm.
The metal will kind of like levitate over it. Is that because of intermolecular forces?
I think that has to do with magnetism.
Okay.
Yeah, that's really more of a physics kind of thing. Mr. Balo could tell you all about that. So size of the molecule or atom is important. Shape is also important. Here we have N-pentane and neopentane. They have the same molar masses. Molar masses is an indication of size because they have the same number of carbon and hydrogen atoms. But here they're connected so that this is more of a spherical shape, and here it's more linear. So this can make this more linear shape, and then these two molecules are going to have the possibility for more surface area contact. These are two spheres, and the surface area contact that's possible is basically just a point. So if you imagine two balls of Velcro and trying to get them to stick together, they only stick at a little tiny point. Whereas if you had two shapes like this covered with Velcro and you put the long sides together, it's going to stick together much more strongly, right? So it's going to take more energy to pull these apart than to pull those apart. So we have molecular size, atomic size, and then we also have shape. When we compare similar elements or similar compounds, molar mass is often a useful guide because that just gives us an indication of size. So any questions about dispersion forces? The next one is the dipole force. Everything has dispersion forces. Dipole forces are present in polar molecules because these are the attractions between permanent dipoles. We talked about polar molecules. Here we have a space-filling model of a polar molecule. One end of the molecule is always slightly negative. The other end is always slightly positive. That's what the permanent dipole is.
So like water?
So, yeah, water. Water is a polar molecule. And so the attraction between these oppositely charged ends of neighboring molecules is going to be stronger than in those temporary dipoles because this force is always present. The dispersion forces come and go, but the dipole force is always there. Those charges are always there. So these are going to be stronger forces of attraction. Polar molecules have dipole forces in addition to dispersion forces. And I put that in there because sometimes we focus on just the strongest force, but I want you to remember that everything has dispersion forces. Here, if we look at two compounds, here's formaldehyde and ethane. And their molar masses are almost identical, which tells us that their size, their physical size, is very similar. When we look at their structures, though, what do you think? Formaldehyde, is this going to be polar? Yeah. In terms of being able to predict whether something's polar or not, we went through all those gyrations and stuff. really, you just have to look at it and say polar or nonpolar. And so here's where my no lone pairs, all the same atoms thing comes in handy. We look at the central atom. There's no lone pairs, but here we have an oxygen and here we have two hydrogens. Those are not the same. And when you look at this, it's lopsided, right? This end is oxygen and the other side is hydrogen. This is a polar molecule. What about this one? It looks very balanced, doesn't it? Now you could say, well, on this carbon, yeah, I've got three hydrogens, but this carbon's different. And this is where I wanted you to remember that carbon-hydrogen bonds are nonpolar bonds, because the polarity difference, or the electronegativity difference between carbon and hydrogen is only 0.4, and so they're considered nonpolar. So if all these bonds are nonpolar, then the molecule has to be nonpolar. So then we look at the boiling points. Formaldehyde boils at minus 19.5 degrees Celsius. Ethane boils at minus 88 degrees Celsius. This boils at a much lower temperature. That means that the intermolecular forces holding these together are much weaker, right? This molecule only has dispersion forces. This is a polar molecule. It has dispersion forces and dipole-dipole forces. And so you have to increase the temperature. You have to increase the amount of thermal energy that the molecules have before they will boil or melt. Any questions?
So like a good example of that is like acetone versus water, like boil.
Yeah, acetone will boil at a lower temperature than water will.
Can you repeat the last part you just said? Like our first question with the weaker the bond.
So if you have a substance with weak intermolecular forces, it's very easy to pull the molecules apart. It takes little energy. And so they will melt and boil at low temperatures compared to something that has very strong intermolecular forces. Higher temperature. Because higher temperature means higher thermal energy, higher kinetic energy. You have to really, you think about the Velcro, you can just really tug on that to get them apart.
So the acetone, his example, is weaker.
Acetone has weaker intermolecular forces than water does, yes. And being able to predict types of intermolecular forces and relative boiling points is another one of those things that comes up a lot in OChem. Another thing that is affected by intermolecular forces is how things mix. So miscibility is the ability of substances to mix without separating, liquid substances. And so we have a saying, we say like dissolves like. This means that if you have two substances with similar intermolecular forces, they are likely to mix together. Not a hard and fast rule, but they are likely to mix together. Here we have a photograph of pentane and water. Pentane and water don't mix together because pentane is all carbon-hydrogen bonds. It's a nonpolar molecule. It only has dispersion forces. Water is a polar molecule. It has dispersion forces and it has dipole-dipole forces, and very soon we'll learn that it has hydrogen bonds. And so these are attracted to each other very, very strongly.
So is it almost like the water molecules on the bottom are so tightly packed together because they're so attracted to each other that they don't let those ones mix between them?
Yep. The forces of attraction between the water molecules are so great that the pentane just can't make its way in. It gets basically pushed out. It's just excluded.
So that's why you could still mix it and they would be separate because you're putting too much energy in the system.
Yeah, when you shake it up, you're adding, this physical kinetic energy, and it'll break into smaller pieces, but it'll never mix on that same molecule level that something that's truly miscible will.
With oil and vinegar, is oil polar or nonpolar?
Oil is nonpolar. Vinegar is actually a dilute solution of acetic acid, and so it's mostly water. Yes?
With polar and nonpolar, I was doing the homework, idea that polar is non-symmetrical
Mm-hmm.
and non-polar symmetrical.
Pretty much.
Going off of that, I got them all wrong.
You got them all wrong.
So,
Well, it's possible that you had the idea backwards, or it's possible that there's another factor in there that you weren't considering. I'd be happy to look at those with you. Any other questions? Okay, so this is a sort of question that could show up on an exam. Which molecules have dipole-dipole forces?
All of them. No, that was the other one, I'm sorry.
Dispersion forces, everything has dispersion forces. Well, before we look at the specific compounds, what types of substances have dipole-dipole forces? Polar. So what we need to do is identify, are these polar or nonpolar? And the best place to start is with the Lewis structure. So carbon tetraiodide is going to have carbon with the 4 iodides around it. I know it looks like Cl4, that's why I wrote the name out. And then there would be lone pairs around all of these iodines, but those don't end up being significant. So the carbon atom has no lone pairs. All of the atoms bonded to the carbon are the same. So yeah, this is most likely a polar bond, but it's symmetrical, right? This makes a tetrahedron, and all the points have the same attraction for the electrons. So this is a nonpolar molecule. Does it have dipole-dipole forces? No.
Well, you said that rule does not always concrete there, right?
That rule does not always work, but it works most of the time. Yeah. Yes?
Can you go over that one more time, why it's non-polar?
Okay, so this is nonpolar because, do you want the long explanation or the short one?
Whatever's convenient.
Well, the short one is that Mrs. K's rule says that it's not polar. There are no lone pairs on the central atom, and all of the atoms bonded to the central atom are the same. It's nonpolar. The longer answer is that if we look at the three-dimensional shape of that molecule, we've got carbon in the middle, and we've got the 4 iodine atoms on the corners of a tetrahedron. It's symmetrical. If we add the vectors for the dipole moments in each of these bonds, they will add up to 0. Okay. So no dipole-dipole forces on that one. How about methyl chloride? Well, here we got C, and there's 3 carbons, and a chlorine. Well, no lone pairs on the central atom, but here we got chlorine and 3 hydrogens. Are all those the same? No. Do they have the same electronegativities? No. So this molecule is polar. Does it have dipole-dipole forces? Yes. How about HCl? There's no central atom. What do we do? Well, diatomic molecule, 2 atoms, there's only the one bond. If the bond is polar, then the whole molecule's polar. What do you think? Do you think hydrogen and chlorine have different electronegativities? Yeah. Even without looking it up, that's a really good bet. So this is polar, and so it also has dipole-dipole forces. Okay? Questions? Third type of intermolecular force, hydrogen bonding. The name makes it sound like it's an actual bond. It's not. What it really is like super dipole-dipole force, right? This is dipole-dipole force, but super, it's stronger, okay? It's the same idea, it's just a lot stronger. So this is found in polar molecules that have hydrogen bonded to fluorine, oxygen, or nitrogen. So it has to be a polar molecule, and it has to have hydrogen bonded to fluorine, oxygen, or nitrogen. Fluorine, oxygen, or nitrogen bonded to hydrogen. Did you see the movie E.T.?
Yeah.
If you haven't, you should. It's a classic. And E.T. says, phone home, right? He sticks his finger out. E.T., phone home. Phone home.
You say it with the accent on.
I know, I've seen it several times. Phone home. F-O-N-H. So that's how you remember what you need for hydrogen bonding. You've got fluorine, oxygen, or nitrogen bonded to hydrogen. Okay? The reason that hydrogen bonding is stronger is that because these bonds are more polar, the charges are larger. The force of attraction is related to the magnitude of the charges. So here the partial charges are larger. So if we look at, this is hydrogen fluoride. So here we've got the hydrogen, here we have the fluorine. Fluorine is really, really electronegative. So this partial negative charge is going to be larger than it was in, say, hydrogen chloride. And because we have larger partial charges, then the force of attraction, the hydrogen bond, is stronger than dipole-dipole forces. Okay? This happens in all kinds of molecules, not meaning that, okay, it happens in lots of kinds of molecules, not all of them, but obviously. Here we have ethanol. So in ethanol, we have an oxygen-hydrogen bond, and this is a polar molecule. Here we've got carbons and hydrogens, and those are nonpolar bonds, and then we have the oxygen and the hydrogen. This is a polar molecule, and it has an oxygen-hydrogen bond. It has hydrogen bonding. So the hydrogen atom with a partial positive charge on one molecule is attracted to, electrostatically attracted to, the partial negative charge of the oxygen on a neighboring molecule. And this is the hydrogen bond. Water does this as well. Here you've got oxygen and hydrogen bonds. That's all that water has. And so the hydrogen of one water molecule is attracted electrostatically to the oxygen of another one. It's not an actual bond. It's not a covalent bond, but it's a stronger force of attraction.
Hydrogen bond is weaker, right?
Hydrogen bond is weaker than a covalent bond. Yep.
But hydrogen bonding.
It's stronger than dispersion forces and stronger than dipole-dipole forces. The reason it's stronger than dipole-dipole forces is because these partial charges are greater. So remember, the force of attraction is proportional to Q1, Q2. So if Q1 and Q2 are bigger, then the force of attraction is greater. The Qs are bigger here because of the difference in electronegativity is larger. So remember that hydrogen bonds are between molecules. Covalent bonds are within molecules. They're between atoms within a given molecule. So hydrogen bonds are only about 2 to 5% as strong as a covalent bond. So they're like 20 times weaker. So that's pretty significant. And what we observe is that compounds that have hydrogen bonds have higher melting and boiling points because their intermolecular forces are stronger. So here we can compare ethanol and dimethyl ether. Their chemical formulas are the same. Their molar masses are the same. But the way those atoms are connected is different. Here we have the oxygen on the end, and here we have the oxygen in the middle. It's not real obvious from the picture there. Just pull it out of the wrapper. So this is what these guys look like. So this guy definitely looks polar, right? Look at this OH on the end, and the rest of this is all nonpolar. This one, kind of up for grabs, whether it's polar or not. This does have, ooh, those are really big. This does have lone pairs on that central oxygen. And so I would expect you to look at that and say, yeah, I think that one's probably going to be polar. And it is, but it doesn't have hydrogen bonding. Why doesn't this have hydrogen bonding? Right, we don't have ET phone home. We don't have this oxygen bonded to hydrogen. There are hydrogen atoms in the molecule, but they're not bonded to the oxygen. Here, we have oxygen, hydrogen bonded together. So we have hydrogen bonding in ethanol, but not in dimethyl ether. They have the same dispersion forces because they're the same size. Yeah, if you have a polar molecule in which you have fluorine, oxygen, or nitrogen directly bonded to hydrogen, there will be hydrogen bonding. Yeah. And so when we compare the boiling points here, ethanol boils at 78, positive 78 degrees Celsius, and dimethyl ether boils at minus 22 degrees Celsius. The difference there is mostly due to hydrogen bonding. Dimethyl ether does not have hydrogen bonding. Well, this is the boiling point. Yeah, the melting points are both below zero. I'm pretty sure I said boiling point, but that's okay. Sometimes I hear something in my head and I say something else. It happens. I like this table. So what are we looking at here? We're looking at the boiling point of these substances versus their molar mass. So this is the group 6A elements, carbon, silicon, germanium, and tin. They all form compounds with hydrogen where they have 4 hydrogens. And we see a trend in their boiling points, right? As the molecules get larger, the boiling points increase. What kind of compounds are these? Are they polar or nonpolar? Let's look at that smallest one. Is that polar or nonpolar? Nonpolar. These are all nonpolar. And so this increase that we see here is due mainly to the increase in the dispersion force. The larger molecule is flabbier, and it's easier to distort the electron cloud and get those induced dipoles. So we see this nice increase. And here we see a trend as well, except for this guy. That looks like an outlier, doesn't it? We would expect that oxygen, its compound, would have a boiling point down here somewhere. But it doesn't. These are the group 4As. Wait, those are backwards. Because it's got hydrogen bonding. It's hydrogen bonding. I hate it when this happens. It's right in the book? Okay, it's probably a slide I got from the previous edition. Okay, yes, these are all polar. Selenium, tellurium, sulfur, oxygen, they're all going to have 2 lone pairs. They're going to have a bent structure. So that's partly why their boiling points are higher than these guys that are nonpolar. Higher boiling point because it takes more thermal energy to pull them apart. The intermolecular forces are stronger. Water is way up here because in addition to dipole forces, it's got hydrogen bonding. ET phone home. And so hydrogen bonding makes this crazy huge difference for water. If it weren't for hydrogen bonding, water would boil at like minus 75 degrees Celsius. That would mess up the planet, wouldn't it? Right? Yeah. So we should be able to answer questions like this. Which has the higher boiling point, hydrogen fluoride or hydrogen chloride? And then that killer question, why? Well, let's think about it. Here, whispered answers. Are these molecules polar?
Yes.
Yeah, they're both polar. So we've got dispersion forces and dipole-dipole forces. Does either of them have hydrogen bonding?
Yes.
Yeah, this one has hydrogen bonding. So here we've got hydrogen bonding. That is a stronger intermolecular force. So these molecules are going to stick together more strongly. Is that going to make the boiling point higher or lower? Higher. So HF has a higher boiling point. Why? Because the intermolecular forces are stronger, because it has hydrogen bonding and HCl does not. Okay? So all of these, which is the higher melting, higher boiling point, etc., you have to look at the individual molecules, identify are they polar or nonpolar. If they're polar, do they have hydrogen bonding? And that's how you're going to determine. Yes?
What about between the phone ones? The FON, which one is the highest?
Well, there's different things that come into play. We're only going to ask you to compare similar molecules. Okay, so if we compare, like comparing alcohols, that's ethanol, and if we compare that, propanol. So here's ethanol and propanol. These are both polar molecules. They both have hydrogen bonding. Well, we need to look for a difference between them. What's different?
Extra CH2.
This one has an extra CH2 in it. So this one is larger. What does that affect? The dispersion forces. It makes the dispersion force stronger.
And that has to do with mass, right?
And that has to do with size, yeah. So this one's larger, so it has larger dispersion forces. They both have hydrogen bonding. And so this one's going to have a higher boiling point than that one. And so when you're comparing, if you've got something with fluorine hydrogen and oxygen hydrogen, you have to look at the rest of the molecule too and see what's different.
Okay, so that was pretty similar.
Yeah, we're going to make you compare similar things instead of, because the other ones, you just don't have enough information or experience to compare. The last one we're going to talk about is the ion-dipole force. This only happens in mixtures. So here we have this happening when we have an ionic compound mixed with a polar compound, such as sodium chloride mixed with water. We get an attraction between the positive ends of the polar molecule to the negative ion, and the positive ion to the negative ends of the polar molecule. And this is the force that accounts for the formation of aqueous solutions. This is even stronger than hydrogen bonding. Here's a nice summary table of intermolecular forces. And so you should know this order, that dispersion is the weakest, then dipole-dipole, then hydrogen bonding, then ion-dipole. And you should know what kind of compounds have these different forces. Hydrogen bonding is really, really important in physiological processes. The other types of intermolecular forces are as well, but hydrogen bonding is what holds your DNA together. Your DNA has two strands, and it's held together by hydrogen bonding between corresponding base pairs. So these are the bases that are present in DNA. We don't need DNA. No, that's not important at all. Thymine and adenine will form 2 hydrogen bonds, and cytosine and guanine can form 3 hydrogen bonds. And so cytosine will always pair up with guanine. It won't pair up with adenine. And so these guys always pair, and these guys always pair. And so you have this double helix, double strand of DNA, where you have all these base pairs matched up, always G with C and A with T. Well, I sometimes forget my biochem terms. I think it's the ribosome that comes along. Ribosomal RNA comes along and splits this up, and then brings in new base pairs and more nucleic acids and replicates a correlating strand. So it's not duplicating this strand, it's duplicating the other strand. It corresponds. If there's A here, it puts T. Over here, there was T, and so it puts A. And so it duplicates and makes two strands from one strand. And that's all because of hydrogen bonding. But the reason that your proteins coil up the way they do and the enzymes function the way they do, it's all about the intermolecular forces.